Hey everybody, welcome back to another year of Young Engineers of Today. I see some familiar names as well as some unfamiliar ones. So I'll just go ahead and introduce myself. My name is Thomas DeToy. The little staff indicator is a liar. My name is not, in fact, David Cato. But that's okay. You can call me Thomas or Mr. DeToy, either one. That is fine with me. Um, Now I know some of these names are familiar, but it doesn't mean you were or unfamiliar, but that doesn't mean you weren't here last year. You just may have not been in one of my classes. So, I guess show of hands, who's back for another year? Who was doing young engineers last year? Okay, cool. All right. Well, welcome back, you guys. I hope you find it interesting. And for those of you who are new here, well, I'm about to go into this whole song and dance that all the veterans have already seen, and I apologize for that. But hopefully, it will still be interesting. We will spend some time going over what we are going to cover this semester, and do some other stuff like talk about engineering, what exactly it entails, and the differences between engineers and scientists, and sort of what's expected, things like that. So let's go ahead and get into official mode here. um, Welcome to Young Engineers of Today, everyone. We're going to talk today about engineering your future. That sounds really super important and official, but it's an introductory class. It shouldn't be too bad. Let's go ahead and get started with some questions. One, do you like to take things apart? I know I do. I like to take things apart. I like to take them apart, I like to try and put them back together, much to the chagrin of my parents when I was younger. I wasn't always that good at that second part. But taking things apart and seeing how they work, things like that, I always found that pretty fun. If you do, excellent. There you go. Got one love to in the question box. Would you find building a game more fun than playing the game? Now, this question can be fudged a little bit because playing games is pretty fun. I'm not going to lie to you. So maybe you find building a game as fun or almost as fun as playing the game, but regardless, on some level, you find building a video game pretty fun. If you do, awesome. Are you curious about how to use solder? Or maybe epoxy? Or how to repair a tent with needle and thread? We're not really going to be doing the tent repairing thing in labs, but you might very well use solder or epoxy in lab. So if you've ever been curious about that kind of stuff, perfect. You should get an opportunity. I don't know if you can hear that, but that's my cat. Get used to it. My cat is going to probably be pretty mouthy throughout the rest of the semester. That is just him introducing himself. Do you enjoy math or science? Um, if you don't right now, that's fine. There might be some point in the future we might find it pretty interesting. Um, it may not entirely be your jam. A lot of people say, "Oh, I'm not really a math person" or whatever. And even if you do want to go into engineering, that may be something that you don't necessarily feel like, and that's okay. Um, I have to admit, I never really considered myself much of a math person, for much of my life. It was actually only in recent years that it really started to speak to me and become interesting. And I think a lot of that can also come down to how it's taught or how you can relate it to real life or something like that. So even if you don't necessarily enjoy math now, I imagine that a lot of you guys probably do, but even if you don't, that's okay. I'm assuming that a lot of you guys are here because you enjoy science. Have you ever, or do you read science fiction or fantasy? I mean, have you ever thought about what the world could be like 200 years from now? Have you ever thought about, like, sort of the fantastic kind of mechanisms that are in fantasy novels and magical things and stuff like that? You ever thought about how those things could be, more realistic? Like there are different levels of what is it, hardness of science fiction. Basically, how much the science has been thought out. Um, on the one hand, you have things like Star Wars, which are more or less like science fantasy. On the other hand, you have Alistair Reynolds novels. You have there's another novel I'm trying to think of, but it's escaping me right now. But there are a few novel writers out there who dabble very much in the hard science fiction, and whether or not it's achievable at this point in human development. But regardless, do you find it interesting to try and puzzle out what it may be like to live with those, how you might make one of those things, or whatever? So now, if you've answered yes to any of the previous questions I've asked, welcome. You are among friends. Friends who like to do mad science and stuff. But welcome. Glad you're here. Hope you enjoy it. And you're not alone. Not that there was ever really any thought that you could be alone, but, you know, it's just good to know. It's good to hear it. Now, this one, the picture is totally covered over what is actually said here, but what it's supposed to say is, what are we doing? Which is a pretty valid question. I might actually say what we are doing, since it's not phrased like a question. Well, regardless, what are we doing is a pretty good question. Well, we're going to learn by doing. I'm sure a lot of you have tried to work out something yourself in order to better understand something that's been explained to you, whether it be, an equation or a diagram of a mechanism or a program or whatever. We're going to try and make this... Hey, Kai. We're going to try and make this as hands-on as we possibly can for the online portion. Now, that's not to say there aren't going to be some points... good to see you again. Weren't you in the middle school last year also? There's not going to be some points in which I'm just going to, talk at you. 'Cause I do that, I admit. Sometimes I just get lost in the rambling and I'd start drawing things in MS Paint. They look terrible, but I'm trying to explain things. But we're going to try and be as hands-on as possible. We'll certainly be very hands-on during the labs. Ideally, we'd like you to help you work towards being a technology creator as opposed to a consumer of technology. Not that there's anything wrong with being a consumer of technology, but it's also kind of cool to know how everything fits together in the end. To be able to look at a phone and go, oh yeah, I understand how the processor sends the information to the memory, and the battery supplies everything with electrons, and then blah, blah, blah. Or I know how the operating system talks to this program and the various things that they pass back and forth, or whatever. We're not necessarily going to go that in depth during this semester, but if the stuff interests you and you continue with it, that is definitely a possibility in the future. Funny thing is, you start taking this stuff apart, it's a lot less complex than it seems at initial glance. And at the same time, it can be staggeringly complex in some ways. Like computer chips, I would never be able to build one on my own. But I understand the basic building blocks that make it up, and in the end, it's actually not horrible. It's complex, but it's understandable. So here's how this is going to be structured. We're going to have class meetings. They call them labs on the slideshow, but you guys will have physical labs. So in order to clear up any confusion, these are going to be classes. The stuff you do with people in person are going to be labs. So we're going to have 1-hour classes twice a week online. Monday and Wednesday at 8 o'clock. Now, I also run one at 5 in case you can't hit the 8 o'clock one. You can go to the 5 o'clock one on Monday or Wednesday and go there too. Also, we're going to start being better about uploading the videos from each class to YouTube. Case in point, I'm actually recording this right now, so everybody look alive, act your best. But But yeah, usually how this is going to work is I'm going to record the classes. I'm going to record both the 5 and the 8, and whichever one kind of I stumble over my words less, I want to put that one on YouTube. So, in case you miss a class, you can always watch that. Or in case I go over something way too fast and we don't have enough time, you can go and look it up on YouTube and watch it again at your leisure. It's going to be no homework. I might say, hey, you guys might want to work on this thing over the weekend so that Monday this can be ready. Or whatever. I might say stuff like that. But if it doesn't happen, it doesn't happen. I'm not going to grade you on it. You know, there's not going to be a note going home to your parents or anything like that. Like, we're doing this to have fun and learn stuff, not to pass a standardized test so that you can get into a college or something like that, you know? So from that perspective, strictly speaking, it's not really homework. It's just sort of like a favor that I ask of you guys that will make my life easier, or, you know, help you guys to cover over some material or get better at something. There aren't going to be any tests either. I might ask you questions like, oh, hey, after all this stuff I just talked about, what might happen if this happens? And it might be a little kind of like quiz on what you know or whatever, but again, you're not going to be graded. You know, I hand out gold stars, but they're imaginary. Um, and it's just relaxed. There will, however, ideally, be a digital portfolio, and what I mean by that is basically a sort of your own kind of space online that you can put pictures of the stuff you've been working on and websites you've been working on and stuff like that, all collected into one place so that you can show it to other people, you know, friends, family. Look at yourself 10 years from now and go, man, I've advanced a lot since then, or, you know, colleges or whatever. So a digital portfolio will hopefully be something we can pull out of this. And those of you who, you know, have done this last year, that shouldn't be anything new to you. Although depending on who your instructor was, I know I wasn't that great about, you know, being like, oh, hey, digital portfolio. But things might change. So the kinds of topics we'll cover. We'll cover civil engineering, specifically bridges, how they work, the physics behind them, what goes into the design of a bridge, things like that. A laser cutter, lasers. You'll be working with laser beams to create your very own cardboard, I'm assuming, cutout. Because as I understand it, cardboard is a chemical process where you recycle paper and doesn't involve lasers. But you might be able to create your own cardboard cutout with a laser cutter. That could be kind of cool because you're cutting with lasers. A trophy head. We'll also be working pretty extensively with the Raspberry Pi, programming in Python, modding Minecraft Pi, music server, game arcade. This is kind of stuff that you can set up the Raspberry Pi to do. Have it be in your house. Like, there are projects with the Raspberry Pi where people have, like, basically taken a Raspberry Pi, loaded it up with a bunch of ROMs and emulators, hooked it up to a television and a controller, and basically made their own home arcade cabinet that can play, you know, like 10,000 games or something like that. And they're all, you know, actual arcade games, like, you know, the Simpsons arcade game, and, you know, Galaga and Pac-Man, and, you know, it's kind of like, that gets into a gray area because of copyright and stuff like that, but you can set it up with games that you do legally own. That would be cool. And then finally, flight. Aerodynamics, the mechanics behind flight, how planes are designed and why they're designed that way, and we might mess around with X-Plane. Who knows? The kinds of software we're going to be playing with, we're going to be playing with the 123D suite of software, which I believe is Autodesk, the free version of Autodesk stuff. So there's going to be design, circuits, and make. Circuits is basically a circuit board prototyper. Design is, if I remember correctly, kind of like, I'm sure you guys have worked with Tinkercad or SketchUp, things like that. Make might be an STL file creator for 3D printing. Might have to look that up. And then also 3D printing itself. Actually, you guys have some really cool 3D printers. They're called Polar 3Ds, and they work by spinning a table as opposed to moving left and right and forward and back like traditional 3D printers. So that's pretty cool, actually. It looks really neat in action. You're also going to be messing around with Code Combat and learning Python. Oh man, who remembers Code Combat? And all of the joys that that entailed. Um, but yeah, Code Combat is a good way to learn Python, so we're going to be spending some time with that. We're also going to be messing around with Inkscape. Um, I'm glad you're excited. We're going to be messing around with Inkscape. We're going to be messing around with a laser cutter, like I mentioned already. Mesh Mixer, which is something I'm actually not familiar with, but I will get familiar with by the time we're learning about it. Just general Python programming, like I said, Minecraft Pi and various things like that. And also a vinyl cutter, which, as the name might suggest, cuts vinyl. Vinyl cutter. Alright. Checklist. I know some of you have already done the whole Young Engineers thing, so you can already do this, but just so we have it, can everybody raise your virtual hand? If you raise your physical hand, that's good for you too. I will not be able to see it though. Alright. Excellent. Everyone's hand is up. Perfect. Now, have you registered for all of the webinars? I really hate that term, webinar. Have you registered for all of the classes? Check with your parents if they handled that. Double check yourself if you handled that. Just make sure you register for everything. Excellent. It might get a little bit wonky in November. Invites might expire. We might have to resend them out, but we'll let you know if that's the case. I'm about to sneeze. False alarm. Have you registered on Edmodo? If you have not, I highly recommend you do it right meow. Edmodo is basically how we're going to be getting all the information to you outside of class. That might be canceled classes, that might be delayed classes, that might be information for upcoming classes that you might need. I know that Mr. Dubik is going to endeavor to get PDFs out of every slideshow that we go over so that you guys can follow at your own pace. This year's class code for Charlotte. Alright, high school. And Kat, are you Charlotte or what's your location? It's not drive.goggle.com. I'm terrible at this. Alright, let's see here. Charlotte. Alright, excellent. I feel like I should have known that already. Alright, let me just go ahead and put the Charlotte High School Edmodo code into here. Send to all. So for everybody, that is the Charlotte's Edmodo code. The Harrisburg one? Sure. Let me go ahead and put the Harrisburg one in there. Copy and paste. Send to all. That one is the Harrisburg one. No problem. I mean, it makes it a little bit difficult to register for the class if you don't have the code, so I do what I can. For sure. Alright, so yeah, if you have not quite yet, go ahead and register on Edmodo right now. For those of you who already have you created your Gmail account? That's another important one. So the Gmail account is good because it's good to receive emails. It's good to have your own email account with which to receive emails. It's also good to... The Charlotte code is invalid. Uh-oh. Because that's the only Charlotte code I have. I do not have any other Charlotte codes. Charlotte High School, right? I'm not losing my mind. The Harrisburg one is also invalid. Oh, thank you, Hudson. Interesting. All right, so Hudson linked. Now, is that the Charlotte code, Hudson? Perfect. So I'll go ahead and put this one here. I appreciate it, Hudson. You really don't have to call me sir there, sir. Though we're just. Unless you prefer it that way. Just try and keep it nice and relaxed. So there you go. Try that one, Charlottes. Charlotteans. Charlotters. Okay, so let's see. Excellent. Glad to hear it, Kai. The Harrisburg one, I only have one Harrisburg one here, unfortunately, Matt. Did you get an email from Mr. Dubik or Mrs. Dubik with a code in it? This is apparently the most updated one as well. Let me check some other places. I might have some, okay. I might have some other places that I can find Edmodo codes. That is not what I was looking for. Alright, here we go. Information. Apologies, checking for it right now. Harrisburg, why don't you try this one? See if that one doesn't work. Excellent. Okay, so it looks like that one worked for Harrisburg. Cool. Alright, back to the matter at hand. Have you created your Gmail account? It's good to have an email account. It's good to have your own personal email account. It's good to have an email account that you can use 10 years from now. I know I had an email account that I created in middle school, and it was great until I started applying to colleges and things like that, and then I kind of realized that that wasn't really one that I wanted to show to adults. It's not really one that I wanted to put on a resume for job searching. Up to you. It just was less work for me to create a Gmail account that I could use. Mine's boring. It's just my first initial and my last name, but at the same time, it's one I can use. Anyway, that's neither here nor there. Gmail account also links you a bunch of other, or gives you a bunch of other stuff. It gives you a YouTube account. It gives you your own personal web space with Google. It gives you the ability to use Google Drive, which is my lifesaver. I'm using it right now. Plus, it gives you the ability to talk to people through Google Hangouts and stuff like that, and the class, and whatever. So if you have, fantastic. If not, you know, maybe work on it so that it's ready by Wednesday. Finally, if you guys could subscribe to the YouTube channel, that would also be wonderful. You know, get your parents' approval first. Make sure they're okay with it. I know you guys are in high school. It's not like you gotta ask your parents for everything, but just as a disclaimer-y kind of a thing. Get your parents' approval. Now, there is an important point about the YouTube channel. I'm sure you guys are at least decently familiar with subbing to YouTube channels. In case you aren't. If you'd like, you can search for Young Engineers of Today. And it's just Young Engineers of Today on YouTube. Just Young Engineers of Today. But yeah, make sure it's got this green robot head symbol here. That's the one, because there are actually two Young Engineers of Today channels on YouTube, and one of them has like a blue icon, one of them has this green robot head icon. We want to make sure we subscribe to that one, because the other one is funky. I don't know, but it's weird. Anyway, those are the things that I ask that you do at some point, eventually, soon. Soon will be good. If you can get it on Edmodo by the end of class today, fantastic. Um, in fact, do that. If you have trouble with it, let me know. If you get on the YouTube channel by the end of today, by Wednesday, fantastic. If you can get a Gmail account by Wednesday, fantastic. Make sure you register for all the webinars too. And we already checked to make sure that everybody could raise their hand, so we already know that one. Okay, the sneeze is actually coming now. No, it's not. This is a sneaky sneeze. Alright, now that we've gotten that done, what is an engineer? Other than this stressed-looking Lego man whose torso is and legs are backwards and who's holding a coffee cup. He's really not having a good day. I guess it's just his head that's backwards. Anyway, an engineer, according to Webster's dictionary, is the practical application of science and math, as in the design and construction of machines, vehicles, structures, roads, and systems. So that's a lot of stuff. I mean, engineers do a lot of stuff, so that doesn't really come as a surprise, but that is a lot of stuff. Simply put, though, it is engineers use math and science to improve the world. That wasn't too bad, now was it? So what makes a good engineer, other than this fantastic invention right here? Well, that's an excellent question. Engineers need to be strong in math and science. They need to be problem solvers who show perseverance, and they need to be able to work as a team and to communicate effectively. Now, it sounds... I mean, like, if you're worried about one of those things, don't worry necessarily. I'm about to go into more detail on them. Engineers need to be strong in math and science. This picture is pretty true once you get into college. You do a lot of studying. But that's okay. Ideally, that studying that you do is actually pretty interesting stuff. It might be dense reading material. That's certainly a thing. There's a fair amount of engineering stuff that is fairly dense reading material. But, on the other hand, if you personally find it interesting, I mean, there are going to be difficult points, but it should still be kind of cool. But yeah, since engineering is the application of math and science principles, it is essential that engineers have a strong foundation in the two subjects. But don't despair. You don't need to be, like, amazing at it necessarily. You don't need to be Superman or Supergirl or whatever in math or science. Different positions do require different expertise. So bridge builders require more of a physics background than chemical manufacturers do, whereas chemical manufacturers are going to be doing a lot of equations and stuff like that. On the other hand, bridge builders need to have a better understanding of maybe which equation to use where, whereas chemical manufacturers may not need to as much. It may be that their equations, while longer, are more of a rote kind of thing. That sounds more derogatory than I meant it, but I didn't mean it that way, I assure you. So they need to be able to work as a team and communicate effectively. And of course, the most appropriate example of working as a team and communicating effectively is Dwight Schrute from The Office. We all know this. He is communication man #1. Really, yeah. A lot of people from The Office are bad examples of working as a team and communicating effectively. But anyway. To solve great problems, engineers of different backgrounds must come together to combine their expertise, and that's true. You have a big project. Good lord. You have a big project, and you got to make sure that everybody's on board. You might need somebody who's good with material science, you might need somebody who's good with, ergonomic design, you might need somebody who's good with mechanisms, you might need somebody who's good, you get the idea. You might need somebody who's good with electronics on this project, you might need a whole bunch of different expertise coming in and working together on this project. So, to that end, you need to be able to not just know the answer, but also to share it in a clear way that others will be able to understand. You might have the best idea in the world. You might revolutionize the face of personal automobiles and be put down in the history books as a visionary. But if communicating your idea can't go further than put on a fifth wheel, stupid, then you're not really going to have a lot of success with that. You're going to make people unhappy around you, and if there's more to the idea than just that, you're not communicating your idea effectively. People aren't totally going to understand exactly where you're going with it. It's really important that everybody's on the same page when they're working on a project, because as projects get larger, there are more details to get lost in, and when people have different ideas of where everybody's going, then it just gets worse, and then suddenly somebody's wearing pants on their head, and it's really confusing. There's a funny little comic that sort of kind of illustrates this in a metaphorical way, because this is something you run into a lot. Now this is more of a programming kind of a thing, but it's the same deal. You could replace "as the programmer wrote it" to "as the engineer built it" kind of a thing. So what the user asked for versus how the analyst saw it, two different things. Doesn't even really make any sense up here. But, they were just misinterpreting what the user was asking for. And then how the system was designed. Well, it was designed, unnecessarily secure. And then as the programmer wrote it, well, things didn't really work out as planned. What the user really wanted. So, as you can see, the user wasn't able to communicate effectively what they wanted, so everything got kind of messed up from there. And then how it actually works is, because real-world situations, best laid plans and all that. So, to go from this to this, where did we go wrong? Really, to go from this to this. They need to be problem solvers who show perseverance. How true. You think. Well, let me put it this way. Engineering and the sciences in general are fantastic ways of humbling you as a human being. At the same time, they make you feel super smart. Both. I mean, at least that's me with programming. I feel like the dumbest and the smartest person alive all at the same time. I feel like the dumbest person alive when your first idea doesn't work. And then when your second idea and your third and your fourth and your fifth and your sixth and your seventh and your eighth and your ninth and your 10th ideas all still don't work, and they all have their own problems. You fix one problem only for another to pop up, and they all don't work. However, you feel like the smartest person in the world when your 11th idea works. And that's kind of how working as an engineer feels. You run into a wall over and over again, and eventually you make progress against that wall. You chip off bits and pieces, and you making a dent in that wall, and eventually you break through, and now you're somewhere. Now, granted, there's a little bit more finesse to it. It's kind of like you tried different methods in order to break down the wall rather than just slamming your head against it, but sometimes it's just slamming your head against it, or at least it feels like it. But regardless, engineering is very much about perseverance. You can't just go, oh, this is never going to work. If you try a couple of times and things kind of fall apart. Because nothing ever goes as planned. If it does, you got to make sure that it's not going to go wrong 3 years from now. But nothing ever necessarily goes as planned. Sometimes it does, and it's fantastic. But just be prepared for that. Just be prepared for the fact that sometimes the road to success is paved with 1 billion headaches. And that's okay. It's still fun along the way. So what kind of jobs are there for engineers? So how I was saying, on a big project you're going to pull in a bunch of people from a bunch of different disciplines and everything like that. Well, there's just kind of this whole spectrum of engineers There's a whole bunch of different types of engineers, like a ton of them. You got civil, you got mechanical, you got electrical, you got chemical, you got aerospace, you got structural, genetic, biomedical, computer, software, military, nuclear, forensic, reverse, and environmental. And that's just kind of some of them. There are tons of different types of engineers, and they all do different things, from civil, who design roadways and buildings, to software, who design programs, to aerospace, who design spaceships and airplanes, and reverse, who take things apart to figure out how they work and rebuild like a copy of it, to nuclear, who build nuclear reactors, and biomedical, who work on the human body and genetically modified organisms and drugs and things like that. It's all over the map. It's all over the map. There are so many fields of engineering, it's insane. And if you have an interest in engineering and an interest in like two other things in the world ever, chances are there's a field of engineering which is applicable. So, there you go. Don't think of engineering as just a guy in a hard hat. Sometimes he's got a hard hat, sometimes he's got a suit and a tie, sometimes he's got a lab coat, and sometimes he's got, not a hard hat. Think about it. But yeah, there are many different kinds of jobs, from hands-on to research to leading a team. We didn't even get into the more leadership aspects of it or anything like that. But that's another thing for another day. So there are some perks of the job. Namely, that right there in his hands. That's wrapped up all of that. This is the median earnings by a major group. Now, median is exact middle. It doesn't necessarily indicate the average. So the median could be 75,000, but there could be the majority of the results are between 50 and 75, or the majority of the results could be between 75 and 100. So you never know. It's basically just the middle point between the highest and the lowest values that were recorded when they were figuring out the median earnings by major group. So for a bachelor's degree, things like agriculture and natural resources, looking at $50,000. Social science, 55. Physical sciences, 59. Health, 60. Business, 60. Computers and mathematics, 70. Engineering, $75,000 for a bachelor's degree. Let's say you decide to go back and get a master's. Agricultural and natural resources, 70. Social, 85. Physical, 90. Health, 80. Business, 80. Computers and mathematics, 89. Engineering, 99, almost $100,000 if you go back and get your master's degree. Think about it. Money. Now, as far as the top 10 college majors that lead to high salaries is concerned, you'll notice that you've got physics and applied mathematics on here, as well as computer science. Now, some fairly self-important computer scientists might say that this is in fact software engineering, but it really depends on your definition. Regardless, physics, applied mathematics, and computer science. The rest of these have engineering in the name. And these are the top 10 college majors that lead to high salaries. The gray line, the shorter line underneath each one, is basically the median salary if you got a job the day you walked off the college campus with your diploma. The blue line, the larger line, is what's expected about midway through your career. Like 10, 15, 20 years in, after you get your job, that kind of a thing. Most of these start out at about $60,000 right out of college. $60,000 a year. Do you know what you do with $60,000 a year? Granted, after taxes, it'd probably be about, $45,000 a year. But still, that's a lot of money. It's a lot of money. Probably, I don't know. Tax math in my head is always a little bit off. Now, about mid-career, pretty much all of these are looking at about $100,000. Which is pretty awesome. That's not bad at all. Now, look at this outlier here, petroleum engineering. Petroleum engineering, you're walking off the college campus, median $100,000. About a decade or two in, $160,000. That's a really decent chunk of change. Now, at this point, we're just sort of talking about numbers. And I'm not here to tell you about, oh, your financial future, and now you should really save up money and go to college so you can get a well-paying job. I'm not going to be one of those guys. We also, it's kind of nice to talk about how satisfying one of these jobs can be. So, I mean, of course, it's easily readable right here, but basically this was a survey where people were asked in different fields whether or not they were satisfied with their job. And it was one of those surveys, if you've ever taken before, that has like probably about 5 grades of answer: very satisfied, satisfied, neither satisfied nor dissatisfied, dissatisfied, very dissatisfied. So, anywhere from 1 to 5, with 5 being very satisfied and 1 being I hate myself. Um, and this is the result of people who basically answered a 4 or a 5 on it: satisfied or very satisfied. Chemical engineering, 54%, right there at the top. Um, Now, that doesn't seem like a lot, but think of pretty much every show you've seen on TV geared towards adults. If you've ever seen The Incredibles, you've ever seen, whatever. Think of how ubiquitous this whole I don't enjoy my job mentality is in popular media. You gotta imagine that kind of thing came from somewhere, right? Now, you can be neither satisfied nor dissatisfied, and that's fine, that's just kind of whatever. But to have half the people who work in this particular field so that they are satisfied or very satisfied with their job, like they either like it or they really like it, that's something. That's really something. It's kind of unfortunate that psychology majors down there are down at 26%. So I know a couple of people who were trying to get into psychology, but they seem pretty passionate about it, so there you go. So about half the jobs that are created today are the result of technology. So, half the new job growth that you see nowadays, new jobs being created so that people can fill them, are the result of technology. On the other hand, many jobs are being lost to technology because of Mr. Robot Hand over here, robot arm. Here's a graph. Look at it. Alright, now let me explain the graph. This is basically split up into 3 different sections, as you can see: low skill, medium skill, and high skill. And these relate to the sort of the skill sets required in order to be able to do the job. Low skill is going to be food prep and productive service, janitorial, personal care, things like that. Medium skill is going to be sales and office administrator, production, operators, and high skill, managerial, professional, and technical occupations. It's also broken up into gender. So, as you can see, the low skill end has been seeing a little bit of job growth, and that's actually just kind of about normal for job growth in general. It's probably actually fair to say that there hasn't really been much of a change at all in low skill. Medium skill, on the other hand, has really seen some issues in the last years. Really. Now, I'll be honest with you, I don't know the time frame of this graph, and I wish I did, because that would be really handy. But I don't know where it came from, because it doesn't have a URL associated with it, and I don't know the time frame. So this could have been the last 10 years, could have been the last 20 years, this could have been the last 15, I don't know, could have been the last 5 years. Could have been since, I don't know, 2014. This could have been a new graph last year. Well, I guess that would have made it since 2013. Regardless, over whatever period of time this is, you've seen a 15% drop for women in the medium skill. That's huge. That's ginormous. Now, on the flip side, which is fantastic, there's been pretty much an equivalent growth in high skilled jobs for women. That's amazing. That's awesome. It's great. But as you notice, high skill has some pretty significant growth and medium skill has some pretty significant decline. And that's really what I want you guys to take away from this, for men and for women. And, well, not so much for men on high skill, but regardless, whatever. There are jobs still opening up. So here's this picture. If you guys did Young Engineers last year, you've seen this picture, and you've probably already heard the explanation. But those blip 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 words, but for those of you who have not, that's a lot of robotic arms, right? Well, all of those robotic arms used to be people. This is a factory that makes electric razors. And there used to be, I don't know, 2 to 3 dozen people at least who worked in this factory. Number I've heard has gone as high as 200. But that's a little insane, but it's possible. It's possible. It could have been 200 people who work here. And if you look at the picture now, there are about half a dozen people. Give or take 2 or 3 people. So that's what we mean, many jobs being lost to technology. I didn't highlight the whole thing. Oh well. Robotic arms came in, took the gerbs. But that's okay, because if you're an engineer, this could be you right here. Or you over here, or you right here, or you way here in the back, or you up here. You get the idea. Being an engineer is a highly valued set of skills that a lot of people look for, even if you don't necessarily get a job in engineering. It shows that you have dedication and commitment, although it's a pretty hard degree to work for to not actually go into engineering, but, you know, regardless. So this is actually the last bit that we have planned, is talking about the engineering versus the scientific method, and I'll spend some time talking about this. And then we will go ahead and I've got a few games that I can link into the question box. I don't know if you guys will find them interesting or silly or whatever. If you do, that's great. If you don't, you don't have to play them. I'm not requiring you to. It's just something, and it talks a little bit about, you know, there's kind of like a Rube Goldberg machine kind of a thing, and, you know, it's a few other things. But regardless, first things first. Engineering versus the scientific method. First, let's talk about the scientific method, and this man here doing what is very clearly science involving hexagons. So the scientific method involves a few steps. You've got observation, hypothesis, experimentation, analyzing your data, conclusion, and peer review. Now, I'm sure pretty much all of you have done the science fair in elementary school or in middle school or whatever. If you haven't done a science fair, you've at least seen the science fair. You at least know what a science fair is all about. That was the whole point of the science fair, was to teach you the scientific method. Also to think critically and to get used to writing stuff and to make nice looking poster boards, and also to, you know, mess around with science. But if you've done a science fair, you're familiar with the scientific method. That is observation, hypothesis, experimentation, data analysis, and conclusion. Peer review wasn't included in there, but you know, people aren't really looking for rigor in a science fair necessarily. So observation is you observe something and, you know, you realize that maybe it's out of the ordinary, or you wonder why it happens. Like, you know, I wonder why cats are annoying. I say that, it's just because my cat's being annoying. And then you hypothesize and you say, well, maybe it's because, you know, cats are from another planet. I don't know. So you make a guess about your observation, basically an educated guess, a reasonably educated guess as to what the answer might be, and, you know, why it may or may not be correct. And then you experiment somehow. It's always different based on what exactly your hypothesis is, but you experiment. You test your hypothesis over and over again, and you gather data. Then you analyze that data. You look at it and you go, well, what does this data say? Does it say that I'm a liar, or does it say that I'm right? Or does it say something somewhere in the middle? With that analysis, you come to a conclusion. You go, oh, well, I guess, cats aren't actually from another planet. That was just sort of a silly thing that I said. And then the big thing is peer review. Peer review is actually a very important part of institutionalized science. Peer review is when a bunch of other professors or researchers or scientists or whatever come together and look at your experiment, see if they can't repeat it, and see if anything went wrong with your collection of data or your conclusions or anything like that. So they look at it and they go, okay, so, he did this. Can we repeat the experiment? Will it provide the same results? Can it provide the same results? Does the conclusion make sense based on the analysis of the data? Does the data make sense based on the experiments done? Does everything check out? Alright, cool. It seems like you scienced good. And that's the big thing. That's what peer review is looking for, is to make sure that you scienced good. Because if you scienced bad, well then, science is sad. Really did not intend for that to rhyme. Anyway, scientific method, ladies and gentlemen. Engineering method is shorter, thankfully. Well, it has fewer steps. I don't know if it's necessarily shorter. Engineering method is research, plan, prototype, and commercialize. So research, first of all, you go, oh, is my super flying hover car viable? So you look at current scientific, knowledge and see if there's something that means that it's possible. Maybe some loophole in physics that allows you to make a car float, or some kind of new material that's light enough that you can fill a car with helium and basically have it be a Zeppelin with wheels. Whatever. So you research, and then you plan. You plan by taking all the results of your research. Emphasis on the wrong syllable. The results from your research. And you create ideas. You go, okay, so maybe Zeppelin cars a go, anti-grav cars not a go. What if we made giant fans instead of wheels? Okay, what if we did this? What if we did that? You brainstorm a bunch of ideas. And then, you pick one. You pick one and you say, okay, let's build this one and see if we can't make it work. That one is your prototype. Prototype is your first working model. Now, there are other prototypes, but prototype is kind of like your first testing model, I should say. It's your first testing model to make sure whether or not it actually works. It's the proof of concept, essentially. And then based on whether or not your prototype works, you might go back to the research stage, you might go back to the plan stage. You might just tweak your prototype and continue from there. Let's say that the car floats, but then it flips over immediately, and then just stays there upside down. You go, maybe we should mess with the gyroscope inside of our flying car. So then you refine the prototype and fix it, and then try it again. Or maybe the car just never leaves the ground, and you go, okay, plan B, Zeppelin car. And you go back to plan, and you build a prototype of that one. So let's say you finally got a working flying car. Here comes the last step, commercialize. Now, this sounds weird and seems like it doesn't really fit, but it's kind of like how peer review is for the scientific method. Let's say you make a flying car, right? But you're the only person who knows how to do it. The way it's built, only you can build it, and it takes you 3 months to build one. Are you really gonna be changing much in the world at that rate? Do you foresee flying cars becoming a thing? Because I don't really. Now, to bring this back to about 100 years ago, the regular plain flavor ground automobile was in much of a similar situation. There was this thing that existed. It was really cool, but it took forever to make, and it had to be made by just a small team of dudes, and they worked forever on it, and cars were just ridiculously expensive. And along comes this man, Henry Ford. Probably recognized the story as well as his last name. Well, Henry Ford comes up with the idea of a car that can be built on basically just a line, the assembly line. just a line, and it moves down the line, and everybody has one thing that they do to it, like, oh, I'm the guy who puts on the bolt right here that makes sure that the steering wheel doesn't fly off and punch the guy in the face. And that's his one job, and he does that. And then, he does his job, and another car moves down, and he does his job on that one too, and another car moves down, and so on and so forth. And they were able to make like 100 of them a day or something like that, which was incredible at the time. Incredible. Because here's the other thing about capitalism. Supply and demand. I'm just going to say it. If there's enough of a demand for something, and the supply is low, each individual thing of that thing, like unit of that thing that you're selling, is going to be super duper expensive. So your flying car is going to be ridiculously expensive. And that was the case for old-timey automobiles. They were ridiculously expensive because they took a small team of specialized dudes to make. Once the assembly line came into the picture and started making these cars, the prices dropped drastically, and now everyone and their mother could own a Model T. And that was really what revolutionized the automobile. It was not the invention itself. The invention itself, while cool, did not actually have that much of a direct effect on the world. The assembly line, however, allowed the automobile to shape, basically, the development of America. I mean, that's why we have everything spaced so far apart. That's why our public transportation is really kind of lacking. That's why a lot of things. It's because of the automobile. So, to recap, scientific method. How can we prove this theory right or wrong? You do background and research, you hypothesize, you do the procedure, you observe the results of the procedure, you analyze, and you come to a conclusion. The engineering design process challenge might be, what can we create to solve this? So you might brainstorm a bunch of different ideas. You might select a design from your ideas, analyze and explain your design, build and test your design, review and decide if your design is the best one possible. And if it is, then reiterate, or redesign based, or if it's not, redesign based on what you learned. If it is, then, find a way to make it, producible at a reasonable value, or whatever is appropriate for it. Anyway, this is one final point, and this is totally unrelated to what we just talked about, but it's actually related to some of the stuff we went over midway through the slideshow, so it might actually be a good thing to go over up there. But regardless, this is the results of a survey done in which employees were asked which attributes they value the most in candidates. Basically, when you're looking to hire somebody, what are you looking for the most? What do you need? And if we start from the bottom, we see, entrepreneurial, risk-taking skills, alright, whatever, it's not running a company, it's working in a company, so I guess it's not really an important sense of humor, creativity, Look at that, fourth from the bottom, GPA, 3.0 or better. Huh, interesting. Meanwhile, from the top, in order of importance, number 1, communication skills. Number 2, teamwork skills. Number 3, interpersonal skills. And then strong work ethic. The first 3 are all about talking to people, working with people, and not making the people that you're working with and talking to angry. Or vice versa. Now, this is not to say that you should not pay attention to your GPA. All I'm saying is the importance of being able to communicate effectively, if you're looking to become an engineer, cannot be overstated. It really cannot. And it's something you'll get better at. But it's really super extra important. I can't believe I did it again. It's 8:59. I managed to talk my way all the way up until 1 minute before it's over. So let me go ahead and put in these games into the question box. If you find them interesting, excellent. If not, no one's gonna blame you. Whoa, 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 whoa. There we go. But regardless, enjoy those. I hereby free you from hanging out here unless you have any questions. Feel free to throw them at me. If not, we'll see you on Wednesday and get the ball rolling on lesson number 1, which should be going over your digital portfolio. But yeah, if you guys don't have any questions, you're free to head out and have a good one.